In the previous video we looked at different sources of energy. In this video we're going to take that a little bit further and start to look at whether or not sources are going to be particularly useful. And we'll start out considering the fact that if a source of energy is going to be used in society, we can't just think about how much energy it's going to produce. We need to be aware of whether or not it's actually going to be economically viable. And that really means that we need to make sure that the amount of money that we spend trying to produce or to mine the source, or to collect the wind that's going to be blowing over windmills or wind turbines, it's going to depend on one or two quantities. So the amount of money that we're spending has to be sort of worth it when considering one of the two quantities that we're looking at here. And as the heading there shows you, the first one is specific energy. Now that word specific, when you see it in a scientific context, basically means that you're dealing with a particular quantity per unit mass. So specific energy then is the amount of energy produced by 1 kilogram of the source. Or not produced so much as released, I should say. The source isn't actually producing it, it's just releasing the energy. And released by each kilogram of the source. And so that's one measure that we can use, so the amount per a unit of mass. Just fix that, each. And the other one then is energy density. So whereas specific energy is to do with the mass, the energy produced per kilogram of mass, energy density is, as the name suggests, is about sort of how densely packed, I suppose. You could say that the energy is in the volume that's going to be used. So in this case it's the energy released by each cubic meter. Of the fuel source. So they sound like they're sort of similar, and in a way I guess they are, but critically the difference is that if you've got a very dense fuel source, then the amount of mass that you're going to consider is going to come into play, whereas if you've got a fairly low density source, then specific energy might actually be one that you want to consider more carefully. Now I'm going to summarize a few examples here, just so we can sort of start to make sense of the significance of these amounts, or these types of quantities that we're looking at here. And again, just a bit of a summary table. We're going to focus on a few common things that you might come across, or that you might have heard of before, and look at both the specific energy and the energy density. So in this column here is going to be the specific energy, and the units that we're going to use here are megajoules per kilogram. And with the energy density, so that we can somewhat make a comparison, even though we're looking at a different quantity entirely, we'll still deal with megajoules, but this will be megajoules per cubic meter. And in the left-hand column here, we're going to deal with the fuel source itself. So some of the fuel sources that we'll have a look at are wood, coal, we'll look at gasoline or petrol, and then a few of the others that are a little bit more common these days as well, so things like uranium in the case of fission. So nuclear fission is what we're really dealing with there. We can look at hydrogen fuel sources, and in this case not the burning of hydrogen, but looking at it from a fusion perspective. Now I'll point out there that fusion isn't actually economically viable yet. We haven't been able to get fusion to be sustainable, and so this is just sort of a theoretical or projected value for specific energy and energy density. And the last one you can see there is if we had water falling 100 meters, so looking at a hydroelectric plant basically. Now, if we want to sort of focus across the way to begin with, so we'll look at each source, and then we'll have a look at the difference between the specific energy and the energy density, and then I want to compare sort of each source in terms of specific energy and energy density as we look down the column. So first of all, if we look at wood, it has a specific energy of 16 megajoules per kilogram, whereas its energy density is 10 to the 4 megajoules per cubic meter. Coal ranges from 20 to 60, so it depends on where you find the coal or where the coal's dug up from. So different sources of coal from around the world, some will have a fairly high specific energy, others will be a little bit less. The energy density ranges from 20 by 10 to the 6 to 60 by 10 to the 6. And for gasoline or petrol, the specific energy is 45 megajoules per kilogram, whereas the energy density is 35 by 10 to the 6. Now, if you just have a look at a couple of these, you can see there's a few little things to identify. Where you've got something like wood that is a little bit lighter, you can see that the difference between the two isn't as significant as, say, gasoline, which would be a more dense substance. Likewise for coal, there's a greater scale factor increase when you consider specific energy compared to energy density. So the how dense the material is itself can sometimes come into play here as well. Now, if we look at uranium in terms of fission, we see a fairly significant increase. So we're now going up to 8 by 10 to the 7 megajoules per kilogram when we consider fission. The energy density is 1.5 by 10 to the 15. So you can see there why nuclear power is something that's used quite a lot around the world. We don't use it in Australia, but certainly European countries, Japan, the US, a lot of those countries do use nuclear power. And you can see the significant increase both in terms of the specific energy when compared to coal and the energy density as well. So some massive benefits in using nuclear power there. Hydrogen in terms of fusion, you'll notice that it's even bigger again. So 3 by 10 to the 8. And then likewise there's a fourfold increase when we look at the energy density. Now the reason for that mainly is the size of the nuclei that we're dealing with. Uranium's quite large, hydrogen's quite small, so as a result when we fuse things together it tends to release more energy per kilogram than what uranium does, and as a result the energy density is higher as well. Now the last one that's interesting to look at is water falling 100 meters, say in a hydroelectric plant. The specific energy, so the energy per kilogram, is actually quite small. It's 10 to the negative 3 because we're dealing with kinetic energy here. It's not chemical potential energy, it's not nuclear energy, it's just kinetic energy, and you can see that it's quite small in terms of the specific energy. The energy density is a bit better, 10 to the 3, but still not as significant as some of those other sources. So there's a bit of a comparison just looking at each source and then making some direct comparisons between the sources as well. There are lots of other sources, and if you want to, you could go and have a look at some of them, and things like wind, for example, natural gas, biomass. Some of those sources would be useful ones to have a look at and see what sort of difference there is comparing to these sources, and both comparing the specific energy and the energy density.